Hello viewers, and welcome to Science Fish Head. You might be wondering, where's the food? Where's the instruments? What's this content here? Well, you see, I'm a high school student. I study natural sciences and all kinds of stuff. So I have a sort of natural fascination towards numbers, mathematics, number theory, all the ways to observe our universe and measure its phenomena. So I thought I would do a deep dive into something I find pretty interesting. Not a deep dive, just a short dive into something I find pretty interesting, which is numeral systems, different numeral systems, the decimal, binary system, and all of those. I will give a brief explanation how they work, how you can convert numbers into others. There's going to be absolutely no reason for you to use this in your daily life, but I find it interesting. You can even learn how to count very big numbers on your hands. Let's get into it with a arbitrary number, let's say 642. Now I do know that this is how you're used to seeing the number 642. This is how you would picture it in your head. You see this number, you say, yeah, that's 642. But that is only one of infinitely many, and I do mean that, infinitely many representations of the number 642, which is just standard for us. You see, each of these digits is actually just a multiplier, which is how every single numeral system actually works. Each of these numbers here, each of the digits 6, 4, and 2, are a multiplier for the numbers 100, 10, and 1 respectively. Let's break these numbers down a bit. So as you may know, and you will know from now on, any number raised to the 0th power results in 1. And going from then, right to left, every single one of these digits represents powers of 10 that increase on the order from right to left. So 6, being the multiplier for 100, is also the multiplier for 10 to the power of 2. Then if we were to add more digits to the left of this sequence, such as a 2, we would end up with 2642, which means that 2 is now the multiplier for 10 to the 3rd power. Then we add a 1, we get 12,642, which means 1 is now a multiplier for 10 to the 4th power, being 10,000. Now, to give more examples, I'm going to want to convert this number 642 into the binary system, which you probably have heard is what computers use, and also what I personally sometimes use to count my hands, which can result in me being able to count to 1023 as opposed to just 10. But more on that later. Now, I don't doubt that right now this number that we've created looks absolutely humongous, but as opposed to the decimal system, where each digit is a multiplier for a power of 10, in the binary system, the 2 system, every single digit is only a multiplier for a power of 2, which means that the second number going from the right to the left, when those are tens in the decimal systems, those are only the 2s in the binary system, the 2 system. And still, the rightmost number is 1, because that is the 0th power, which always equals to 1. And the second number going from the right is the number itself that the system, the numeral system, is named after, being 10 in the decimal system and 2 in the binary system. So as you can see here, the way we construct 642 in the binary system is we lay out all these zeros, which will first represent nothingness, but in different powers of 2. We give them all multipliers that then eventually add up to the number we want. And because this is the binary system, our only choices are 1 and 0. 0 being absence and 1 being presence. There's no added quantities. You only have an on and off switch, whether for example 2 or 4 exists or not. What this means is that the number 642, we start off with 512. It's going to be easy to tell that 512 is the largest number from all the powers of 2. That is still less than 642. we give that 1 as a multiplier. The next number, 256, is not going to fit, so we give that 0, so we make space for the other numbers. 128 will fit, which then leaves us at 640, and we skim past all these other numbers, these powers of 2, until we reach what we have left, which is 2 to the power of 1. All these numbers are still only powers of 2, and just by adding up different powers of 2, we can actually create any number in existence, but it will be a very long string of digits. So now, all of these systems do share logic also in the way that you would count upwards from 1, then 2, 3, ... What you do is you add up numbers going from 1 until you reach a digit that is the number that the numeral system is named after, because that is already exceeding then the maximum digit that you can even see. For example, in the 10 system, decimal system, there is no such number as 10. There's no single symbol that represents 10, because 10 is then represented by the next one being 1, 0. That's how you write 10, because there's no ones, but there's 1 10, which is 10 to the power of 1. I know this sounds confusing, but then you add that logic to the binary system. The way you'd count is you take 1, the next time you reach 2, which means you already have to carry that over, and then you have 1, 0, which looks like 10, but now you realize that that number can't objectively mean 10, because now 2 different numbers are that. So if you write 10, but then mark that as the binary system, it's only going to be 2. At every point, you're going to then add 1 to the rightmost number, but if it becomes a 2, you carry that over as a 1 space left. And anytime that there's 2 1s in the same spot, you keep carrying over to the left until there's free space. I can demonstrate this with my hands. Visualizing this using your hands is actually shockingly uncomplicated. You start with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, although the ring finger is quite hard to hold up here. Alright, enough with these easy baby numbers. How about we do something truly silly and go for a 7 system perhaps? Now by now I hope you realize that this number does not equal 1605, rather a string of digits that goes as follows: 1605, representing in this situation multipliers for different powers of 7, because who would like an easier number? Going past the displayed numbers would result in some pretty stupid looking numbers, but as we know, the 0th the power of 7 is 1, then the first power of 7 is 7, the second power equal to 7 times 7 is 49, you multiply that by 7, you get the third power of 7, which is 343, and so on. What this means is we now have a multiplier of 1 for 343, which means we have, 343. Then 6 times 49, at which point I don't remember how big of a number we have, perhaps 637, which means we're only missing 5, which means we're going to have a multiplier of 5 for the ones, which means 1 times 343 plus 6 times 49 plus 5 times 1 equals 642 in the decimal system. And even if we aren't working with just counting your fingers, as in one finger is 1, 2 fingers are 2, which is how children count the primitive way, or just counting ones and zeros the binary way, I'm not gonna tell you that my fingers are able to bend into 7 different positions, but perhaps I can demonstrate finger counting in a tertiary system, as in a 3 system. And it goes as follows. If you have flexible hands, you can also use the joints on your fingers as notches and count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now for the 7 system, your hands might not be the optimal counting tool, but as a little exercise, you can take something small like pebbles or just random junk you have, small items like dice perhaps. You put them in an area designated to ones. You start stacking them or gathering them, get 1, 2, 3, 4, 5, 6, and you know the next number would be 7, but it's the 7 system. You can't have 7 ones in the 1 section. You're going to condense them all into having a 1 in the 7th section, which is directly to the left. And after that, you'll have free space to start counting your ones again, and this would be 8. And so we've come to the end of this video. I really hope that after all this educational content, the idea you have of different numeral systems, like the decimal system and binary system, and also alternate odd systems, is a bit more clear, and you can maybe even try counting binary with your very own fingers and see how high you can get before you get bored, because I don't think you're going to be reaching the very end unless you're a very dedicated person. And with that, I hope my unexperienced scientific ramblings didn't bore you to death, and this video is just playing next to your corpse on autoplay on your phone, and you actually managed to enjoy and learn something that you may use. Have a nice day, and until the next video.